Welcome to the weekly lecture series. Today we have with us Professor Nathaniel Calculus, who thinks deep thoughts all the time. Today he will be speaking on his recent paper on the Euclid mission. Welcome, Professor Calculus. Professor Calculus, welcome.
Hello.
Excellent. I'm glad you're with us here. Now, for those of us not quite part of the space community, can you tell me what this is? What is a mission and what is the Euclid mission?
Well, a mission is something where you're trying to achieve something. So the Euclid mission is trying to achieve scientific goals. So it's trying to find more things out about the universe, and it's going to do this by going up into the air in a rocket, and then going into space, and it's a satellite. So it sits in space.
Oh, it's a satellite we're talking about.
Yes. I believe it sits at a Lagrange point, which means that it's sitting at a position in space where it's stationary relative to the rest in the solar system. So that it's one of the points where gravity is sort of canceled out. So it's going to sit up there so that it's stationary, and it's going to look all around the universe and try to find the dark energy and dark matter in the universe.
Oh, thank you, Professor Calculus. Fascinating. Tell me, how does this mission, this Euclid mission, expand scientific understanding of the Earth and the universe in which we live? Can you tell me that?
Well, Euclid is a mission designed to further our understanding of the nature of the acceleration of the expansion of the universe. At first, it seems hard to believe that the rate of the universe's expansion is increasing, or even that the universe is expanding at all. What happened to the fundamental force of gravity that we all learned about in elementary school?
I don't know. Is it gone?
No, it's not gone.
Oh,
Shouldn't gravity be at work here?
That would be bad.
Well, there's another force. It's called dark energy. And it comprises of roughly 68% of the energy in the universe.
68%?
That's the mass energy. So you combine the mass and the energy in the universe, and you get the mass energy of the universe.
Wow.
And 68% of the mass energy total. So dark energy is thought to permeate all of space, and although its mass energy equivalence is very low, so it's spread very thinly throughout space, its total presence is very large. Not much is known about dark energy. It is spread so thinly that despite the fact that it's all around us, it's difficult to measure its properties.
All around us.
Regardless, dark energy is causing the rapid expansion of the visible universe, and measurements taken from Euclid will help to accurately calculate the speed of this enlargement and its acceleration.
What is Euclid?
Euclid is the mission we're talking about right now.
Oh, sorry, okay.
There are several ways to do this, but the simplest is by measuring redshift.
Redshift. Sounds like a nightgown.
Yes. Redshift occurs when a wave is stretched, much like the Doppler effect, except in this case, the wave is light. And light cannot be stretched in length because light is always traveling at the same speed. It's a constant. The speed of light is constant. So instead of stretching in length this way, light stretches in frequency. So the wave spreads out to this. By measuring the amount of stretch, you could say, in the wave, we can tell how fast the source is moving away from us. By using this technique, we can measure the speed that objects are traveling away from us and the direction they're traveling. The speed and the direction
I'm starting to understand.
Are the velocities, and by measuring the velocities of the objects, we can measure the amount of dark energy in the universe.
Wow.
The second dark thing that Euclid searches for is dark matter. Dark matter composes of 26.8% of the mass energy in the universe. So that's a lot.
That is a lot.
That leaves only
sounds awfully scary.
4.9% for normal matter and normal energy.
Wow.
So dark matter you might think would be dark, like this coal. But
I can't see it. Can you open that up?
The dark matter is more like the bag the coal is in.
Oh.
Dark matter is called dark matter because it doesn't radiate or emit light, and it also doesn't change the path of light that goes through it, other than the gravitational effects. So it's essentially transparent. It's like a sheet of glass. We can't see it, but we know it's there because its gravity is present. But the light, the only way we can look at things in the universe that are far away is by looking at their light, and there's no effects on the light other than the effects of gravity, because gravity is present on light also. So we know the dark matter is there, but we can't really tell what it is. So scientists are going to use this mission to try to narrow down their choices.
This is the
dark
Euclid
matter.
mission.
Yes,
We're back to the
mission.
Euclid mission. Okay.
So they have several ideas. They're not really sure. They think it's probably not one of the fundamental particles that we've already determined.
Oh, so something new?
So it's something new that they haven't found at CERN.
Oh, very
Yes.
exciting,
Excellent.
Professor Calculus.
So they think it's probably a non-baryonic particle, and the baryons are the particles that we found so far. So it's probably something we don't understand, and that makes it interesting.
That does indeed make it interesting. Something we don't understand is always something interesting.
So the dark matter is also present in large quantities in the universe, and it was first discovered a really long time ago when astronomers first noticed that galaxies were being held together, but they didn't have enough matter to be held together. They were sort of, the gravity was there, but the matter wasn't there. So they knew there was something missing, something they couldn't see.
But something was out there holding
Something
it all
was out
together.
there. So we're still not really that much closer to finding what dark matter is, but this mission should help us because it'll map out the locations of dark matter and its densities in those locations, so maybe we can figure out where the dark matter is coming from, if it's coming from a star, if it's the source can help us assume what it might be.
Uh-huh.
As you might see in a rainbow, the
A
colors
rainbow?
Yes, the rainbow. The colors red, orange, yellow, green, blue,
And violet.
are present. So violet has the shortest wavelength and therefore the most energy because there are the most of the waves in the color violet. And red has the longest wavelength of the visible spectrum, so it has the least energy. So as the wave stretches, it stretches from a violet color, if it were violet to begin with, to a red color as it stretches out. So you might ask, how could we figure out the frequency of the source? How do we know what the wavelength is to begin with? So stars emit light based on their composition. So the light differs from star to star because different stars have different compositions. The light produced in a star is produced when the electrons drop an electron level, and each atom, each type of atom, so each element, has a different way of doing this. So the different light frequencies are produced by different types of atoms producing different spectrums of light.
I got it. I'm getting it. I'm starting to understand.
We know the spectrums produced by each element, so if we look at the star that's producing the light, even if it's shifted, we can notice a pattern because there are different types of stars, and so we can match the type of star that goes with this star even though it's been shifted, and then when you match them together you can measure the shift.
I see. Okay. Thank you, Professor Calculus.
The third and final thing that Euclid wants to look at is the early conditions of the universe. So we know something, we've predicted things about the early universe with math, and we've observed some things, but we haven't observed a lot. So you can observe the early universe because the universe was at first expanding and may still be expanding faster than the speed of light.
Wow.
So the light is being emitted, and the sources, as it's being emitted, are being stretched out. So it may travel, the sources may at first be 20 light years apart, but as time progresses and it travels those 20 years, the sources may stretch to like 80 light years apart. So the light doesn't actually reach the destination. So this light has been stretched out since the beginning of the universe, and we can observe it if we look really, really far away and see the conditions of the early universe based on this light, the frequencies and so forth.
So those are the main three options for Euclid.
Yes.
Well, thank you, Professor Calculus. That was fascinating to see what Euclid's mission is all about. Can you tell me what are the fundamental science questions being posed that this mission intends to answer, in addition to what you've already discussed?
Of course. First, researchers wish to determine, is dark energy merely a cosmological constant as first discussed by Einstein, or is it a new kind of field that evolves dynamically with the expansion of the universe? Alternatively, is dark energy instead a manifestation of the breakdown of general relativity and deviations from the law of gravity, according to the Euclid Consortium?
Oh,
Essentially,
consortium, huh?
Yes, indeed.
Bravo.
Essentially, this is saying that researchers wish to discover the true nature of dark energy, and they have several ideas about what dark energy might be. The first option for its existence is that it is a cosmological constant. That is, it's present everywhere in the same quantities, and it comes sort of tags along with space.
Is that what Einstein believed?
Well, at first. So we usually think of space and nothingness as synonyms, but in reality they're very different. In space, even when it is empty, time passes, while nothingness has nothing. The idea says that in addition to time, all space contains a mysterious energy that fights gravity and causes everything to expand. It is always present, hence the word constant. The second option connotes that dark energy is a field, like the Higgs field, which gives mass to all of our subatomic particles, or the gravitational field, which gives everything.
Now it's all crystal clear to me.
Yes, causes gravitation. So the difference between a constant and a field is that the field can differ in strength. So a constant is present everywhere in the same strength, and a field, it can change. So the field could be stronger in one place and cause everything in that place to expand more rapidly, or it could be non-existent in some places and cause them to be subject only to the effects of gravity. So we can tell whether something is a field or a constant by the rate of expansion, because if we see some really big differences between the velocities of things going away from us, we'll know that it's a field because there are differences in the dark energy composition. And if we see things all going away at the same rate or all going away at a rate that's constant, we'll know that it's a cosmological constant.
Yes, that seems to make sense.
So the third option would be, alternatively, is dark energy instead a manifestation of the breakdown of general relativity and the deviations from the law of gravity? So I'm not really going to go too complex. But
tell me.
Scientists are asking whether, instead of their previous theories, this is some kind of like anti-gravity. Not really anti-gravity, but the opposite of gravity. So it would be forcing things apart instead of pulling them together. The identity of dark energy is the first of the important questions that Euclid hopes to answer.
Whoa!
The second important fundamental science question, according to the Euclid Consortium.
Darn that consortium.
Yes,
they must be
wonderful.
smart.
Yes. Is what are the nature and properties of dark matter? So that's the coal, but not the coal, the bag.
The bag, but
Yes,
not the
the
coal.
bag.
Yes, indeed.
Yes. So like dark energy, dark matter is something that's a fundamental part of our universe, but also one that we don't understand. So we talked about some of the ideas for the identity, and Euclid should be able to help us identify what dark matter is, or at least narrow down our choices. So the identity of dark matter is another one of the
fundamental science questions.
Yes. And they hope they'll be able to do this by graphing its distribution and densities in those places.
So those are the two fundamental science questions?
Oh, no,
or are there more?
There are more, indeed.
Oh, tell me.
The third question that the Euclid mission hopes to answer is, what are the initial conditions which seed the formation of cosmic structure? It will attempt to answer this question by looking almost 10 billion years into the past. So that's, we're talking about looking at the light that was emitted at the beginning of the universe. So this isn't really the beginning of the universe. This is 3.8 billion years after the beginning of the universe. But that's still fairly early.
That was a while ago, I'd say.
10 billion years ago. So they're going to look at the light from that time, and they're going to try to figure out how all of the cosmic structures, the galaxies, the stars, the matter we see has formed from the energy at the beginning of the universe, or the Big Bang. And by doing that, they'll hope to see what might happen in the next 10 billion years of the universe, which should pertain to us all, since we're all going to be here in 10 billion years.
Maybe.
And they want to see what the expansion of the universe will be at that time and the distribution of matter. Because some people think that dark energy may just take all of matter and split it apart into its little subatomic particles. And just, the universe will be a soup of subatomic particles at one point. Because the dark energy will be...
Are you sure, Professor Calculus?
Yes.
A soup?
Yes, a soup. That's what they call it. Of subatomic particles, because the dark energy will have driven everything apart. It will be so strong that they'll overcome all of gravity, and even the bond, the strong force between in the nucleus of the atom.
Professor Calculus, this is fascinating stuff. So can you tell me, what is the connection between this Euclid mission and the science mission directorates?
Well, I'm glad you asked.
I'm sure you are.
The Euclid mission will address 2 of the 3 science mission directorates.
Oh.
Astrophysics. So that's 2 out of 3.
Wow.
Yes. It will answer the questions, how does the universe work, at least in part, and how did we get here, by researching the origin and destiny of the universe. Although, I don't think it will answer the 3rd question, which is, are we alone? But you never know. We might get lucky.
You never know. So, Professor Calculus.
Yes.
Yeah. You've basically laid it out in pretty serious terms, but are there other reasons why this mission is important?
Well, I suppose the answer to that question depends on what you find important.
Yeah.
I mean,
it might be very different from what you find important.
This mission is important to me because I am interested in the answers to the questions, but it might not be important to you because you might not have any interest in the workings of your universe.
Oh, such an assumption. Professor Calculus, I'm sure there have been previous missions. Can you tell us about some of the ones that and what this mission is built upon?
Well, actually, there haven't been too many previous missions in this field.
Oh.
This mission builds upon all of the previous research into dark matter and dark energy. That doesn't necessarily mean it's a mission into space. So you can look at this stuff from, say, balloons in the Arctic. So evidence of cosmic expansion was first discovered in 1929 by Edwin Hubble, and it shocked the scientific community because they thought either gravity was pulling everything together or the universe was in this state of equilibrium and everything was just staying the same distance apart. They had no idea that this would be happening.
Mm-hmm.
So, in fact, Einstein referred to his failure to predict the expansion of the universe as his greatest blunder.
Oh.
In 1980, Alan Guth and Alexei Starobinsky suggested that a negative pressure field similar to what is now known as dark energy could have driven the expansion of the early universe. Proof of dark energy's existence, however, did not come until 1998. The Boomerang and Maxima experiments validated these 1998 observations in 2000. The existence of dark matter has been known a little bit longer. Fritz Zwicky inferred it when he noticed a large deviation between the observable mass of a volume of space and the gravitation it produced. So that's the galaxies. He saw that the galaxies were being held together, but he didn't really know why, because there wasn't enough observable mass for them to be held together.
Mm-hmm.
Dark matter was confirmed in the late 1970s when astronomers observed a similar phenomenon. So the theories that this mission wishes to test are fairly new. They're within the last 100 years.
Well, that's pretty exciting.
And the previous research it will elaborate upon has been either theoretical, they like their math,
mm-hmm.
or measured with more inaccurate equipment. In 1929, they might have the same equipment as us.
I can only imagine.
So this mission will study concepts that are on the brink of our understanding, so we don't really know anything about dark matter or dark energy.
That's very exciting. So, Professor Calculus, what are the connections to NASA, to colleges and universities, and other international program missions? What agencies or organizations do we need to collaborate with in order to develop the mission itself? Is it extremely complicated? Is this what part of the consortium is?
Yes, the consortium.
Euclid consortium, the aforementioned Euclid consortium?
Yes. This mission has been a collaboration from the start. Although Euclid is a European Space Agency-led mission, NASA and the Euclid Consortium are both crucial partners. The Euclid Consortium is an organization that amalgamates over 1,100 researchers, engineers, and technicians that directly contributed to the Euclid mission. So
That's
this
amazing.
Involves people from the space agencies to the world's leading universities. There are a lot of international universities. And groups such as the CERN or the Smithsonian are also involved in the Euclid Consortium.
So that's pretty exciting. So it's a worldwide endeavor, you might say.
Even the Netherlands Organization for Scientific Research has joined. That's how prestigious it is. So the Euclid Consortium is essentially in charge of the mission, although the ESA is officially in charge, so it's sort of iffy. The ESA has selected Thales Alenia Space to construct the satellite and service the module, and Airbus Defence and Space to create the payload module, but the Euclid Consortium is also performing construction.
see. So, Professor Calculus, if you were in charge of the Euclid mission, who of these, how many, 1,100 people would be on your advisory board? Or would there be someone else?
Well, I'm not really sure. That would be a difficult question because there are a lot of scientists and engineers and technologists that are interested. So I would definitely have several experts in the scientific field.
Well, that's
dark matter,
probably a
dark
good
energy,
idea.
theoretical physics, and so forth. And then I would have some engineers because, of course, you can't have the mission if you don't engineer the satellite.
Indeed.
Finally, I would have
You never
some,
get off the ground, you might say.
Yes, that's sort of difficult. Finally, I would have a mission planner and a financial advisor.
Oh, financial advisors are always important these days.
Yes, that's what I've noticed.
Which is one reason I think this is probably such an international endeavor, is it not? So you can have financial backing from all over the world.
And people are interested in this.
Yeah. So, Professor Calculus, you've gone on and on and on, some might say. But can you tell us what kind of data needs to be collected and how it's relevant and how are they going to collect this data anyway?
Well, to answer the science questions, data needs to be collected that will allow the researchers to determine the distribution and identity of dark matter and dark energy.
I've heard scientists like data.
Yes, they do. This mission utilizes 2 or 3 different instruments to gather this data. The first type of data that will be collected during the mission is information from a visible instrument. This is essentially a camera. But it's a specialized camera because it produces very high quality images and very high resolution images. It operates much the same way as your camera on your phone does, but is equipped with a filter, so not all of the light can get in. It's only a specific portion of the light.
So a special camera.
Yes, with wavelengths between 550 nanometers and 900 nanometers, which is 1/1000th of a meter.
Oh my goodness.
So this is
That's pretty amazing.
This short light.
Yeah.
Yes.
Yes.
This system will measure the shapes of galaxies and derive the effects induced by gravitational lensing. So gravitational lensing is when gravity causes light to bend. So we know that photons, while energy-carrying particles, still have mass and therefore are still subject to the effects of gravity. So every once in a while, a massive object in the universe, say a black hole, will cause light to bend, and by looking at that, say the object is dark energy, or not dark energy, dark matter, we can determine where the dark matter is by looking at where the lensing is. Because if the observable stuff isn't very massive, but we see a lot of lensing of the light, we'll know that there's some dark matter there because...
Lensing or bending?
Bending. Well, they're the same thing.
Oh.
It's called lensing because a lens bends the light.
I see. Professor Calculus, you are so smart.
Yeah.
Continue on, please.
So, with these measurements, both the current distribution of dark matter and distribution up to 10 billion years ago can be determined, because we know the light coming from us wasn't emitted today. If something is 580 million light years away, the light is 580 million years old, without the effects of the expansion, which we talked about.
Yes,
Sort of
yes.
complex. Yes.
I understand that concept. I'm with you.
So, the data is relevant because by analyzing it, we may be able to determine the identity of dark matter.
Yes, indeed.
By
That's what
searching
we're
for the
hoping.
conditions of its formation. The second instrument, it's number 2.
After the camera.
Yes, that will contribute data to the Euclid mission is actually a combination of 2 instruments. That's why I said 2 or 3. Called the Near Infrared Spectrometer and Photometer.
Good Lord, couldn't they come up with a shorter name than that?
Yes, they call it NISP.
NISP?
They like their acronyms. It collects data at the wavelengths between 1,000 nanometers and 2,300 nanometers. The first instrument is the photometer, an instrument that collects data on the intensity of light. So that's how bright the light is. So in wave form, that would be the magnitude of the wave.
I see.
So this instrument is essentially an extremely specialized camera as well. It aims to collect near-infrared photometry of the same galaxies observed by VSCS to determine the photometric redshifts. So it's just, yes, this is another way of determining the redshift. So we talked about how you can look at the spectrum. This is another way, instead of looking at the spectrum to determine how much it's changed.
Oh.
Looking at different frequencies.
Okay, I think I'm following you.
The second instrument is a spectrometer, and it does the things that we talked about, looking at the gaps in the spectrum to determine the type of star that the light is coming from, and then looking at matching that star and looking at how much it's changed.
Uh-huh.
But in addition, the spectrometer can determine the chemical composition of the source, and it will be able to derive more accurate redshifts of the distances of galaxies. So not only can it do the redshifts, but it can look at the distance that the galaxy is away from us. And it can determine the galaxy's three-dimensional position in the universe.
My goodness. So it can do quite a bit, the spectrometer.
Indeed it can. It's very versatile.
I see.
This data will aid researchers trying to find the distribution and identity of dark energy.
That's a lofty goal, I have to say. That's very interesting, Professor Calculus. And who will make use of the scientific data that's collected?
Well,
I imagine quite a few people.
That's often the scientists that make use of the scientific data.
That's kind of where I was going to go with this. Anyone other than
most of the
scientists?
people that will use the data are members of the Euclid Consortium. However, the data collected will be relevant to all physicists and cosmologists.
Cosmologists.
If I can manage to pronounce that.
Not cosmetologists.
The discoveries of the mission could amend the laws of physics. So
wow.
It's a big goal. But
that's a pretty serious goal right there.
So that would be relevant to a physicist. The mission users, in this case, are not really members of the general public. I don't think you're going to be looking at the redshift data and saying, oh, that's exciting. I'm glad they put that up there. No, it's really going to be the researchers looking at this. And then,
but if it changes the fundamental laws of physics, it's going to affect everybody.
But you're not going to be the one that discovers that it changes the fundamental laws of physics.
Well, you might have a point, Professor Calculus. So where can we obtain historical data for this project, if available? Is there somewhere where we would get this historical data?
This project really hasn't been launched yet, so it's difficult to have historical data for a mission that hasn't actually begun yet.
Oh. Well, I guess that makes sense, Professor Calculus. I'll give you that much. So, does society benefit from this mission, or is it just a whole bunch of international money spent on nothing?
Pointless things.
Pointless space stuff.
Well, society does benefit from this mission because they reap the rewards of an increased understanding of the universe. If we had never discovered electricity, we would have never had electrical things such as lights or motors or cars, any of that stuff. So we don't really know what dark energy and dark matter could lead to, but we know that we don't really understand them. So with new understanding comes a lot of new things. So we could use dark energy perhaps to find a new way of propulsion that could take us to new places such as other stars. We could find dark matter and use it for different things depending on its properties.
Mm-hmm.
Yeah.
All right. So basically, can you tell me what the applications are of this mission and how it's going to improve the quality of our lives? Or is that all based on what we find and we won't really know till we find that stuff out?
Well, the Euclid mission is not an undertaking focused on Earth. It's really an undertaking focused on the universe.
Yeah.
So we don't really know. It's not really going to improve your health, or but it probably will find new natural resources, because if we find what dark matter is, it's probably going to be useful since it's managed to evade.
So it might improve my health through various new uses in the future, but you never know.
There's a future serum made out of dark matter that saves your life one day, Mom. Economically, this mission brings together a lot of people. As you heard, the Euclid Consortium. So that increases global awareness and therefore global understanding, which is always good.
Indeed. It sounds like it's a great collaboration.
And they've been outsourcing to smaller companies, so when commercial spaceflight does ever come around, we should have more resources to come upon.
Okay, thank you, Professor Calculus. So basically, you've given us a lot of information, a lot of scientific information. To get down to the nitty-gritty, why should taxpayers spend money on it? I mean, how does this connect to real-world concerns in an economy that's already struggling in a lot of countries?
Taxpayers should support this mission because it is fundamental to developing an understanding of our universe. This is like the Large Hadron Collider run by CERN. It is unlikely to affect you in your day-to-day life, yet the implications it could affect the entire race overall. So you're not going to see immediate results. It's not going to have the first wave of data and you say, oh, we now have a new type of car that can go 500,000 miles per hour. No, it's not going to be like that. But you will be rewarded technologically by the things that this mission finds. And if we make predictions into the future of the universe, it is going to affect us all because we're all in the universe. Some would argue that this mission connects more to the real world than what you are considering the real world. So we're just on Earth, but Earth isn't really that much in the universe. It's just sort of there.
Oh, Professor.
It's just there.
It's just there, huh?
Yes. So the Euclid mission is studying things that are far more essential to the universe. So the stuff that it's studying makes up 95.1% of our universe, and yet we know nothing about it. Some would argue that that is important to figure out.
Would you be one of the people that would argue that?
Yes, possibly.
Quite possibly. Well, thank you, Professor Calculus. It's been a pleasure to speak with you. Are we done? Oh, we're not done. Is there more?
Yes, Mom.
Professor Calculus, so who are the stakeholders of this mission, and what are their perceived beliefs about the missions and its priorities? Are they all the same? How does this work?
Well, the beliefs are never really the same in everybody, but the stakeholders are mainly people from the Euclid Consortium, who are therefore directly involved in the mission's planning, and these researchers may dedicate years of their life to making this mission a success, so they must perceive it as something of importance.
Indeed, I hope so.
Yes, I don't know. Most of the scientists, most of the stakeholders are the scientists who are trying to decipher the laws of nature.
Those 1,100 people in the consortium?
Yes, well, not all of them are scientists. Some of them are engineers.
Engineers as well.
Yes,
I see.
But they must think that Euclid is the best way to do this.
Indeed, if they're putting so many years of their life into it. And so what are the considerations built into this mission from the stakeholders themselves?
Well, the stakeholders are members of the Euclid Consortium for the most part.
Yeah.
And they help to design the mission, build the mission. So they have a pretty influential role in the development of the mission. And they can pretty much change the mission to meet their needs. For example, the data that is collected is transferred directly to the members of the consortium, so it isn't transferred to other places to be processed. They get the raw data to analyze.
So they can use it
So the
as
mission
they will.
has been designed and will be operated by the consortium. Actually, it's 50% the consortium being operated on the ground. So when they send the data to the ground, 50% goes to the consortium to be analyzed, and 50% goes to the ESA.
What's the ESA?
The European Space Agency. So that's the collaboration between all of the European
Union
Yes.
participants.
So they design the mission, and they will be operating it, so they're pretty much in charge, and they're the stakeholders.
I see. Professor Calculus, one final question to wrap up this terribly invigorating and intellectually stimulating interview that we've enjoyed this afternoon. Your bow tie's a little crooked, Professor. Is the Euclid mission going to become a reality? What's the time frame? Is it launching like next week? What's happening with that?
Well, not quite next week. It's due to be launched in the first financial quarter of 2020.
What's the financial quarter?
I don't know.
Oh, you're an astrophysicist. You don't know about the financial.
The financial quarter, it was like, I don't know, it was sometime to April 6th, or maybe it was March 6th. It was the 6th. I remember 6th.
Okay.
I don't know. I would assume it's a quarter.
So do you think it's going to happen?
Yes, probably.
Okay.
They've already started building it, in fact, so I think it's likely to happen.
Way?
I don't know if it'll happen then, because these missions often are bumped back and back and back. But it'll probably happen sometime in the near future.
That's very exciting. Thank you so much, Professor Nathaniel Calculus. We were so stimulated by your exciting lecture, and we wish you the best in your endeavors.